Good morning. In this lecture video, I am going to explain a decimal arithmetic. So, in the previous video, I explained addition of single byte and multi-byte addition. Now, we'll see how we can perform a decimal arithmetic operations. So, as we know, human beings are familiar with the decimal numbers, but microcontroller performs operation in binary. So again, 8051 application involves in adding intelligence to the machines. Their hexadecimal number system works naturally, but when the application involves interacting with the humans and humans are familiar with the decimal number system, it is convenient to use decimal number system to represent the numbers used in programs. And we know 4 bits are required to represent the decimal numbers, that is 0 to 9. That means 4 zeros to 1001. And these numbers are often called as binary coded decimal numbers, BCD numbers. So, I mean, two BCD numbers can be packed into single byte of data. Since it is an byte means 8-bit 8-bit data, no? So, two numbers can be stored in a byte location. Let's see, 8051 does arithmetic operation in binary. So when BCD numbers are being used, the result may be non-BCD. Non. Let's consider an example. 49 and 38 in BCD. Why we call it as a BCD? It has only digits 0 to 9. 0 to 9. So you are expecting the result 87. Again, that is also in BCD. Here 9 plus 8 17. 17 means 1 7 1 carry. Again 1 plus 4 5 plus 3 8. So we won't consider as a hexadecimal. But microcontroller performs in binary. That means in, so we treat this as 49H and 38H. Here H means hexadecimal. Hexadecimal. But digits which are used is 0 to 9. Okay, so we treat these are the BCD number even though extension H is there, but microcontroller treat this as hexadecimal. In such a case, suppose in binary, so 49 will be written as first to 4 bits 4, that is 0100. Next is 9, 1001, and similarly 38, first 4 bit 0011. Next 8 means 1 followed by 3 zeros. So this, so in a red color we call it as a lower nibble, and in blue color we call it as an upper nibble. Okay. If it is done in binary, this is how, see, 1 plus 0 1 0 0. Here 1 plus 1 0, carry 1, carry 1, and we call this carry is auxiliary carry, because it is from the bit 3 or from the lower nibble. And again here 1 plus 1 0, carry 1, again 0, carry 1, 0, carry 1. Right? So in, it is in binary. In hexadecimal it is 8 and 1, but we expect the result 87. We expect the result 87, even though 81 is a BCD, it has only 0 to 9 digits, but result is not correct. So microcontroller gives the result 81 along with the carry flag is set to 1. So this 81 will be stored in A register and carry flag is set to 1. So we need to adjust the result. We need to adjust the result. What's that adjustment? We need to add 6 to the lower nibble, since auxiliary carry flag is set to 1. Okay, we add 6 to the lower nibble. So when you add 6 to the lower nibble, it becomes 7. 7. So it is 87. So we consider this as a BCD, correct BCD. So what we supposed to do? We should to adjust the answer, we should add 6 in decimal to the lower nibble, or we can say 06H. So here nothing is added means we can say 0 is added. So 06H to the result, since auxiliary carry flag is set to 1. And we'll consider one more example. 68 plus 24. You are expecting the result 92. But in microcontroller, it performs as 68 plus 24. In binary, it performs like this. This is 6 and 8, 2 and 4. Okay. So if you do it in binary, it is 0, 0, 1, 1, 0, 1 plus 1, 0, carry 1, again 1 plus 1, 0, carry 1. Here it is 1. So upper nibble is 8 and lower nibble means 1, 1, 0, 0 means 12, that is C. So here directly you can observe 8 plus 4, 12. 12 means C. Okay. But 8C is a non-BCD. 8C is a non-BCD. Right? So to adjust the result again, we add 6 to the lower nibble. 6 to the lower nibble. So microcontroller gives the result 8C. Even though auxiliary carry flag is 0, since the lower nibble is greater than 9. So we add 6 to the lower nibble. If you add 6 to the lower nibble, see 0 plus 0, 0. So 0 plus 1, 1. Here 1 plus 1, 0, carry 1. That will be added here. So 0, carry 1. So that will be added here. So now it becomes 9, 2. Okay, now it is correct BCD. Correct BCD. So to adjust the answer, we add 6 to the lower nibble or 0.6 to the result, since lower nibble is greater than 9. That is C. Similarly, we consider one more example, that is 7682. So you are expecting the result 158. That is 6 plus 2, 8. 7 plus 6, sorry, 8, 15. In hexadecimal, sorry, in microcontroller, 76 plus 82 means it is 8. Correct? 6 plus 2, 8. Here 8 plus 7, 15. 15 means F. And similar it is in binary. Binary. Even though auxiliary carry flag is 0, okay, carry flag is also 0. Since upper nibble is greater than 9, we add 6 to the upper nibble. 6 to the upper nibble. Okay. Right now, when you add 6 to the upper nibble, see, this carries as it is. Otherwise, you can add zeros here. Zeros here. And here see 1, 1 plus 1, 0, carry 1. Again, triple 1 means 1, carry 1. Double 1 means 0, carry 1. So this will be considered as a most significant digit, that is 1. So now the result is, it is 5 and it is 8. 5, 8 BCD with the carry. And this carry will be considered as a most significant digit, is 1. Okay. So what we did to adjust the result, add 6 to the upper nibble or 60 to the result, since upper nibble is greater than 9. Okay. And we'll consider one more example, 98 plus 71. You are expecting the result 169. So in hexadecimal it is, so 8 plus 1, 9. Correct? And here it is 7 plus 9, 16. 16 means 1, 0. So 0, carry 1. So now even though this is 0, 9, correct? 0, 9 is a BCD, but result is not correct. So if you consider this as a most significant, so it becomes 109, but we expect the result 169. That is why we add 6 to the upper nibble. So it is in binary. Since carry flag is set to 1, even though it is BCD, result is not right because carry flag is set to 1. So actually microcontroller gives us 09 with C is equal to 1. And so since carry flag is set to 1, we add 6 to the upper nibble. If you add 6 to the upper nibble, the result becomes 6, 9. Result becomes 6, 9 with carry 1. I mean previous carry. Okay. So now this carry will be considered as the most significant digit. Then together it becomes 169. So what we did to adjust the answer, 6 to the upper nibble or 60H to the result is added since carry flag is set to 1. Clear na? So from these 4 examples we observe that this decimal adjust accumulator instruction adjusts the sum of two packed BCD numbers in A, leaves the adjusted number in A only. That means adds 0.6 to the result if lower nibble is greater than 9 or auxiliary carry flag is set to 1. Okay, what it will do? Decimal adjust accumulator instruction Actual operation is adjust the sum of two packed BCD numbers in A. If it is non-BCD, it adjusts into a BCD and leaves the adjusted result in A only. What it performs? It adds 06 to the result if lower nibble is greater than 9 or auxiliary carry flag is set to 1. And second operation, it performs adds 60H to the result if upper nibble is 9 or carry flag is set to 1. So this is the two main important operation done by decimal adjust accumulator. That means if carry is equal to 1, if the adjusted number exists, 99, otherwise it is a 0. So again it uses auxiliary carry flag and binary sum of individual binary nibbles. So auxiliary carry flag has no other use for to the programming. Only for this purpose we use auxiliary carry flag to adjust the result into a BCD. And one more important point, it assumes odd numbers were in BCD before addition was done. So adding hexadecimal numbers and then using DA will not convert the sum into BCD. And one more important, this decimal adjust accumulator instruction adds with only odd instruction or RC instruction and does not give correct adjustment for some multiple multiplication or division instructions. Clear now? So this is about decimal arithmetic instructions. So I'll continue in the next video. Thank you.